Hello, am I audible?
Yes, sir. Audible, sir.
Okay. Just a second. It's getting disconnected for some reasons. Give me 2 minutes, okay? Somehow I have to take care of this. Yes. Is my screen visible now? I hope it is. You are able to see the screen, right? Okay, I'll assume you are able to see it. So, welcome everyone to the week 10 session uh, of the course Fundamentals of Semiconductor Devices, NPTEL NOC25 EE-39. So, the course instructor is Professor Digvijayan from IIC Bangalore, and I'll be the TA for this session. Uh, I'm a PhD student at IIT Kanpur. So, the schedule for my sessions, as usual, is every Sunday 3 p.m. to 5 p.m. So, I'll try to communicate it early, but next week we won't be having this session, the tutorial session at 3 p.m. Sunday. We'll have it before that. Okay, we'll have it around Thursday or Friday. We'll see. You'll be communicated by the NPTEL NPTEL portal. Please make sure you are tuned to that. So the guidelines, as usual, you may raise your hand if you have any. I guess I should write that as well. Let me write it here. Next session, Thursday or Friday instead of Sunday. Okay. Now, as usual, the guidelines. In case you have any query, you can uh, ask it in the chat window, or you can raise your hand. Please ensure that your microphones are muted, especially when you don't intend to speak. I'll try to make this an interactive session, and for that, I appreciate your cooperation. Uh, Please keep pen and paper handy along with a calculator. And yeah, the recording link for this session will be shared by NPTEL course team in the due course of time. And In the last week, following topics were taught by the course instructor. Okay. Uh, Solar cell basics were discussed, and then uh, Shockley quasar limit was discussed, and the basics of this photo detectors were also discussed. And then
So one minute,
we had,
1 minute. Another question.
okay,
Uh, if I miss the uh, examination due
uh,
to some reason, then can I prepare for the next time, or any uh,
I mean, are you asking
reference?
about is there any possibility of a makeup exam? Is your query on those lines?
Uh, yes, sir. Uh, if I unable to attend the examination
Uh,
due to some reason, then examination uh, next
See,
then sir,
there is only
for
one
next time.
examination for this course, right? If I'm right.
Yes, sir. Yes,
There
sir.
is only one exam scheduled for this course, right?
Or another time is not given.
Okay, so only one
We-
single
we-
timing has been communicated to you, and you are saying that if you some for some reasons, if you miss out on that, will you be able to give
Yes, sir.
exam, right? So,
Yes, sir.
see, as far as I know, for certification examination, giving examination is mandatory and important, and even I guess the major chunk of the percentage uh, in order for you to secure a certificate would be devoted to this examination. So what I would suggest you is uh, when is exam scheduled, by the way, first? When is exam scheduled?
Uh, 27 April.
27 April, right? So you have around 1 month. Uh, so do
Yes,
one thing, mail the NPTEL course team at your end. I mean, I'll also uh, try to see if I can reach out to them. But it would be better if you, uh, I mean, mail them and uh, tell them that. But by the way, why do you think you won't be able to attend the exam? Any reason? Any particular reason?
due to sir my job, sir.
Okay, okay, okay,
Uh,
okay, okay. I guess you should mail the NPTEL course team and tell them that this timing won't be convenient for you because I mean it clashes with your job schedule. So, is there any alternative? I guess there would be. I mean, they would come up with some alternative. I mean, that's just my assumption, but it's better that you ask them on mail and get a written confirmation for the same. Is that fine?
yes, sir. Thank you, sir.
No. Okay. So it's better you mail them early. I would suggest you to mail them today or tomorrow itself. Okay. So coming to the prerequisites, in the last weeks, the following lectures were taught. Uh, the solar cell was discussed, basics of it and its working, and the Shockley quasar limit was discussed. Then photo detectors, the figure of merits and types of the devices were also discussed. And lastly, we saw a discussion on junction photo detectors. Okay, so firstly, what I would suggest, just a second. So before starting this one, what I have planned is uh, in heterojunction, or I should say the compound semiconductors tutorial, I recapitulated, right, some topics. So my plan is that I would do the same for this solar cell as well. And then uh, I'll utilize, there would be one extra session. Okay. So after 12 live sessions corresponding to the 12 weeks, there would be one extra session, and I will pick some problems from compound semiconductors and some problems from this last week's content and show it together in an extra session. Okay, will that be fine?
Yes, sir. Fine, sir.
Okay, okay. Because the thing is, we won't be going into much depth in compound semiconductors and solar cells. That's why I was planning to utilize one session that would be an extra session, and I'll cover them both. And as far as this solar cell is concerned, what we just a second. So, do you have any idea, I mean, how solar cell works or which region is of interest in a solar cell? So suppose I take an example of silicon cell, right? Before that, what are the types of solar cells that were discussed or touched apart from the crystalline silicon solar cell? Sorry. So the types of, maybe I should say right, types of solar cell. Okay. We have crystalline silicon solar cell, right? And we have amorphous silicon solar cell. We also have organic, right? Organic solar cells, and we have some junction solar cells like gallium arsenide, indium gallium arsenide. They are also uh, one type. And I should write multi-junction for this, right? And what else? We also have perovskite oxide solar cells. Okay, perovskite oxides. Right. So these are the type of the solar cells. Fine. Also, so what is the basic principle that is, I mean, uh, taken advantage of in a solar cell? Did you go through last week lectures?
No, sir.
Okay, please do go through them. Okay, so let me
Okay, sir.
show this. So this is your, say, PN junction, right? And what you do is, suppose there is a wire. Obviously, after taking out the contacts, so there would be an associated depletion region, right? We will have a depletion region here. This is boundary, and this is the depletion region. Now, suppose I'm shining a light, right? Suppose there is a light source, right? And you're shining light on this. So which region is of interest in this PN junction? I'm assuming
Sir,
you do
Einstein
know, right?
photoelectric.
See. Once
Sir,
you
Einstein.
once this light falls on this PN junction, so what happens is that your electron hole pairs are generated, right?
Produce,
Electron
sir.
hole. They are generated. And depending on the region, if the region has an electric field or not, they are swept. And the movement of those electrons and holes as a result of getting swept by the electric field constitutes the current, right? So this would be the direction of
Yes,
your solar cell current. Okay, now my question is, PN junction has two types of regions, right? You have quasi-neutral region on N, quasi-neutral region on, sorry, quasi-neutral on P, quasi-neutral on N, and then you have depletion region in between. So which region is of interest? I mean, uh, which is the region on which when this light falls, uh, the electric field is present? Or in other words, which region has electric field?
P region, sir.
Depletion region, right? And thus, when light falls, see, your electron hole pairs, they are generated in both your quasi-neutral region and your depletion region. But the thing is that we don't have electric field here, right? In quasi-neutral regions, we don't have electric field. So uh, the electron and holes in the depletion region, they experience electric field, right? And they consequently get swept by that, and that is what your this current is. And then we can use this current for many applications. So this is basic rough idea of uh, what should I say, the working of this solar cell. Okay, then let me see what I can show. Also, we also saw that, see, this is a semiconductor bar, right? This is your semiconductor bar, and there would be an associated band gap, right? You will have some EG, band gap of that semiconductor, where this band gap would be the difference between your conduction band and valence band lengths, right? This would be your EG. So now this EG will have an associated wavelength, right? If I call that, say, lambda, right? What would that lambda be? Do you remember this relation? E is h nu. Does this seem familiar?
Yes, sir.
Right. And what is frequency in terms of lambda? I hope you must have seen this relation. Your C is your lambda times frequency.
Yes,
Okay,
sir.
you're
Yes, sir.
right. And if you rearrange, you'll obtain that your E is h c by lambda. Right. From this, I get this. Hc by Eg would be my lambda, right? Absorbed lambda. So your photons, uh, see, this light would be comprised of photons of different lengths, right? Different wavelengths. But only the photons that would have the lambda corresponding to this Hc by Eg would be efficient, right, in generating electron hole pairs, right? Eg or greater than Eg, right? So that would be, just a second. So see, if you have a photon that is greater than Eg, even that would result in electron hole pair generation. So in terms of wavelength, what I can say is, if your lambda is less or equal to this Hc by Eg, that would be the region of interest, or I would say the wavelength spectra for which your electron hole pairs would be generated. beyond this point, if lambda is greater than this, that would result in an energy, corresponding energy that is less than Eg. And that won't be sufficient to generate electron and hole pairs. Is this clear? Is it making sense what
Yes,
I'm
sir.
saying? Okay. So,
Yes, sir.
so that's why this is the spectra that we make, that this is your PSD, right? Your y-axis is your PSD, and this is your lambda in nanometer. And there is some peak, right? This peak is this lambda, right? So suppose I mark it by lambda naught. This is your lambda naught. This is a lambda at which your this absorption electron hole pair generation process is most efficient. And uh, just a second. Yes, I missed it. This is your lambda naught, okay. And say suppose your lambda naught falls somewhere around here. Beyond this lambda naught, right? If your lambda naught is greater than this region, this won't result in electron hole pair generation because the lambda values, the corresponding lambda values will be less than Eg, right? And as such, the energy won't be sufficient in taking, say, electron from conduction band to valence band. Sorry, valence band to conduction band. Okay. So this is
Yes,
your
sir.
what? This is your spectra. What else? Uh, so this would be the fraction of the photons that are not absorbed. And this will be the fraction of photons that are absorbed, right? Absorbed in the sense that they result in electron hole pair.
Sir,
Yep.
uh, can you explain this operation one more? I have a network issue, sir. If possible, sir.
Okay, sure. Should I repeat it again?
Yes, sir. Yes, sir. Yes, sir.
Okay. So, from what point should I repeat? So let me rephrase it again once again. So, so the thing is, I was discussing the basic principle or the basic working of a solar cell. Okay. Say we have a p-n junction. I'm taking an example of a p-n junction, say crystalline silicon p-n junction. And when light falls on it, or I could say photons fall on it, uh, we have two regions in p-n junctions, right? What are those two regions? Could you help me?
Yes, sir. Yes, sir.
There is a
There are
region.
two regions.
Yeah.
Region
There are
is
two
called.
regions.
Yes, sir. One is bulk. One is interface, sir.
Yeah. Or let me rephrase your answer. There is a region where the electric field is present, right? And that would
Yes, sir.
be this depletion region, right? Because remember how we draw the this like peak electric field at the interface, right? Or at the junction. And this particular region, this is your depletion region, and electric field is zero in which region? Quasi neutral, right? So this in this and this, your electric field is zero. Okay, so I'm not having any electric field at all in these regions. And this is the region where electric field is present. Is that fine?
Yes, sir. Yes,
Okay.
sir.
I guess I'll also do one thing. I'll make a band diagram also. That would make this more clear. Okay. Say suppose I make a band diagram for this. Let me move this a little lower. Suppose this is your Fermi level, right? And what would be
Yes, sir.
your this depletion region would be where this E has a slope, right? This portion. Notice you are having constant energy here and here. So this
So
region,
there is ab- absence of potential, sir.
absence of,
A-
I would say
Electric field, sir.
absence of
Electric field.
electric field. Yeah, absence of electric field.
Yes, sir.
So firstly, tell me which region is this one? Which region is this? Is this P or N?
P type, sir. P type.
P type, correct. Because this is your what? EC, this is
Fermi
your
level is near
EV.
to the Fermi,
Yeah, correct, correct,
Fermi
correct, correct.
level is
So
near to the
that's
valence
why,
band.
correct, correct. This is your P type and this is your N type, right? And this is your depletion region, right? The speciality, or I should say, the difference, how depletion region differs from your quasi-neutral regions is the fact that you are having this slope, right? Slope in energy, and that uh, I would say translates to having an electric field. Because remember, if your bands are bent, that is an indication that electric field is present. Here, bands are not bent, and you can conclude that E is zero here, right? Similarly, E is zero here. Why? Because bands are not bent. If I remember it correctly, your electric field, does anyone remember the expression relating electric field and your energy, band energy? It depends upon the slope, right? Your electric field, if I denote this by this E, this is 1 over Q dE by dx. This can be anything. I mean, let this be C or V or I don't care. I mean, any of the three, right? So the idea is, let me take C. Okay. So this is your electric field, and your electric field is zero here and here, right? And in this region, your electric field is non-zero. Why is it non-zero? I'll take the magnitude only. Okay, let's take the magnitude. So the electric field is non-zero in this region because this is non-zero here, right? There is a finite slope. It's non-zero slope. So as a consequence of that non-zero slope, you'll have a non-zero electric field. And because of that non-zero electric field, see, now let's, uh, what should I say? Let's come back to the picture. What was happening? You were uh, throwing photons, right? You were throwing photons. Wait, let's take this a little. If I'll go fast, just let me know. Okay. So these were your photons, right? We also show them by H nu, right? We are shining this, right? We're shining this here. We're shining this here. I mean, it's falling everywhere, right? So the photons that, what do photons do? Photons would impart energy to the electrons so that they become free. In other words, an electron, see, you'll have this electron that is here, right? You, you impart if this photon is of sufficient energy, this would impart the electron energy high enough so that this becomes free and comes here, and it will leave back a hole. Do you agree?
Yes, sir. Yes, sir. So, sir, as per you say that photon can create some photon can create energy to the electron, which
Yeah,
can
photon actually
free to
provides energy. See,
yes,
even
photon.
if you think this via thermodynamically, see, you need some energy, right, for this electron to go from valence band to electron, and photon is absorbed in providing that energy. Okay, so your one photon is absorbed and one electron moves from this to this, provided that the wavelength of your photon is less than this. That is where this discussion was all about. Okay, why am I saying so? Because it will be easier if we talk in terms of energy. Suppose I give you a photon that is of energy Eg. Will that be able to excite an electron from valence band to conduction band? Yes or no?
Yeah, no, sir.
Why?
Sir, more than EG. More than EG, sir.
Okay, take even EG. I mean, EG is also sufficient.
Okay,
Okay.
okay, okay, sir. Okay,
So
sir. Okay,
EG
sir.
is fine. And as you correctly pointed out, even more than EG is also fine. Right. But what if the energy of the photon is less than EG? Will the electron be excited in that case?
No, sir.
No, right. And if Eg is less than, so suppose photon had an energy E. If your E is less than Eg, right, what would be Hc by E? Relation between Hc
Sir,
by Eg and Hc by E?
sir, if the EG is more, as per your concept, EG is more, sir, lambda will be less.
Right. So this would be the relation, right? So
Yes,
the
sir.
photons uh, for which this E, okay, if my photon carries an energy that is less than the band gap, what is this quantity dimensionally? This is wavelength, right? So the wavelength, the
Lambda.
corresponding wavelength of that photon would be greater than this Hc by Eg. So all those photons that have a wavelength that is greater than this Hc by Eg will not be absorbed, right? So this is that fraction. And all the photons that have,
Sir,
yeah,
sir, one more time, sir. If the photon energy is more than band gap energy,
yeah,
as per your concept, if photon energy is uh, less than band gap energy, so uh, these are will be uh, count free the electron.
no, no, no. I guess you got confused. See,
Yes,
if
sir.
I'll repeat it again, if my energy is greater than Eg, absorption will happen, right? Because electron will have sufficient energy to go there. Even if it's equal to, say, roughly Eg, even then, electron will have sufficient energy to overcome this barrier of Eg. But
Okay.
if your energy is less than Eg, the band gap energy, your electron, suppose this is half of Eg, right? Your electron will have, say, the energy imparted into the electron will only be sufficient to take it to here, right? But that won't be enough, right? To free it,
Yes, sir. Yes, sir.
right? So this won't happen. That's why for these energies, the absorption of photons won't happen. And this translates to your lambda being greater than lambda naught. For these lambda, your photons won't be absorbed. So this is actually a reverse of this, right? E less than Eg, absorption won't happen. Lambda greater than lambda naught, absorption won't happen. Okay, because your energy is inversely proportional to wavelength,
Wavelength.
right?
Wavelength.
Yeah,
Yes, sir. Yes.
that is the reason we see this relation. So is this clear now? Now coming back to this. So we don't have electric field here. We don't have electric field here, but we do have electric field here. And in which direction is electric field here? Is it from left to right or right to left? Okay.
Sir,
Remember,
left to right, left to right, sir. Left to right, sir.
no, no, no. It's not from left to right. The electric field would be from right to left. The reason being because electric field always points in a
Opposite to
direction
the
where
electromovement.
bands are upward. Yeah. So this would be the direction of your electric field. This is your electric field. I mean, we hardly care about the magnitude. The idea is the direction would be this. So now tell me, your electron reached here, right? What is this? This is conduction band in the depletion region. What will happen to this electron? This would experience this electric field. In which direction would this electron go?
Sir, from left to right, sir.
Left to right, correct. So this would move here, right? And this won't be the only electron. I mean, I just showed you one such example. There would be many, right? So the movement of electrons, right? Let me write it. Your movement, or I could write transport. Let me write whatever it is. Movement or transport of electrons that we just saw is from, okay, let me just
Uh,
make this
Left to right,
direction.
left to
It's
right.
from left to right, right? Okay, this is
Yes.
done. What about holes now?
Opposite, sir.
It would be opposite, right? Because the holes, they would move in the direction of electric field. So your
Yes, sir.
movement or I would say transport of holes, as you just said it would be from right to left.
Right to left.
Yeah. So now tell me, both these result in a current, right? And what is the direction of that current?
The direction of current, sir, in the whole direction, sir.
Right. So it's from right to left, right? Or in other words,
Yes, sir.
current flows in this direction, right?
Yes, sir. Yes, sir.
That's why at the start I showed this, right? It's from P to N. And if you notice, this is opposite to the direction in which forward biased PN junction current flows in. Okay, so this is opposite to that direction. That's why I'm not sure if the instructor has discussed a mathematical model of solar cell. Has he discussed it?
Sir, yes, sir. I think, sir, I have not view every lecture, but I think,
Okay,
sir,
okay,
there will discuss, sir.
okay. So the thing is, there these two currents, your diode current, sorry, the PN junction current and ISC current, they would be oppositely on it, right? This is the main reason
That's why, sir.
why.
That's why, sir. Is VI character line third zone, sir. Means is
Yeah. That is, yes, that you can, I mean, relate it with that as well. So now, just a second, let me see what else can I show you. Is this part clear? Whatever I discussed?
yes, sir. Yes, sir. Yes, sir.
Okay.
Sir, before that, if you discuss anything, sir, I have joined in late, sir.
I'm not sure what did I discuss. I guess I had a short discussion on types of solar cell. That
Okay.
your
No, that's
solar
not.
cells, yeah, you have crystalline silicon solar cells, amorphous silicon solar cells, organic solar
Organic solar
cells,
cell.
yeah,
Sir,
multi-junction, peros, yeah.
sir, you discuss this everything in
No.
when.
I mean, I just
In,
pointed them out. I did not
okay.
discuss one by one all of them.
Okay.
Okay, one more thing that I have to show you. See, your PN junction, this particular thing, right? It won't be in this manner, right? I have drawn a 2D image of this, right? In 3D, what you'll see is, uh, okay, see. If you, I mean, in real applications, or I would say practically, what will happen is you'll have the P side of this, right? P side surface. Let me draw the top view of what you guys would see. You'll see this P, right? And the depletion region would be, you remember these two directions? This is going into the plane, out of the, sorry, this is out of the plane direction, right? And this is into the plane, right? So
Yes, sir.
depletion region would be into the plane, okay? Because you have to travel from, I mean, this is the top view, right? So you have to travel P in order to reach depletion region. And the area of this, whatever this structure is, the exposed part would be only this much, right? So sunlight will fall only on this. Right? It will have to go through this P and ultimately reach here. Okay. So what would you,
Sir, dot and cross convention once more, sir.
I did not get your point. Could you repeat it again?
That dot and cross circle.
Yeah.
So inside the field is cross, sir. Inside the field is cross.
Sorry. My bad. Thank you for pointing it out. Yeah, this is the cross one, right? Into this, right? Your depletion region would be into this. So tell me one thing. Uh, if your sunlight falls on this, you'll have, uh, say, many, there would be electron hole generation, right? Your photons would be utilized first in this quasi-neutral region, right? Because for first sunlight has to pass through this quasi-neutral region in order to get to this depletion region. So what would you prefer? Would you rather prefer to have this quasi-neutral region thin or thick?
Thin, sir, thin.
Thick? If your answer is thick, I need an explanation for that. And if your answer is thin, I
Sir,
need an explanation for that as well.
sir, actually, my answer is thin, sir, thin.
Okay, thin.
The
And
main
why is that the case? Why should this be thin? Why should this be thin?
actually, sir, actually, if this is thin, sir,
Huh?
the energy can reach to the actual depletion region and create some electron holes, sir.
Correct. I would rephrase this and make it a little, make the answer a little better. So what you are saying is, if this is thin, the major fraction of these photons would reach depletion region, right? And only few would
Yes, sir.
generate electron hole pairs in this. Because see, the generated electron hole pairs in the quasi-neutral region, they are of not interest. I mean, we hardly care about that. Why? Because electric field is not present there, right? This is region of
Yes,
interest.
sir.
The electric field is present in this region. So we would prefer that this be thin, as much thin as possible. And also one thing, if you have this sufficiently thin, then we run into different problems, right? We'll have high sheet resistance, and to tackle that, uh, we dope P heavily. Okay, just remember this much. And I guess the instructor would have discussed the rest in way more detail than I would. And let me see what else can I show you guys. Having this description. Sorry, this
So, yeah,
screen is not
green.
visible. Yeah.
Yes,
I
sir. Yes.
just noticed it. Okay, is this now visible?
Yes, sir. Yes, sir.
Okay, then we probably, I mean, I went through the
Sir,
contents. Yeah,
sir, I just want to know that uh, in your first page, second page, in where you write the cross and dot convention.
yeah,
Uh, Cross means, sir, inside the field and dot means outside the field.
yes.
Sir, it is a convention or it can be
I mean,
some
this
extra.
is the convention that is usually followed. I mean, uh, I guess this is the convention that is, by the way, accepted everywhere. I have
Okay,
not
okay, sir.
seen
Okay,
a book where this dot represents going into the plane.
okay, sir. Okay.
Yeah, just give me a couple of minutes. Okay, I'll see what else is there that I can discuss. So this is basically the basic of these solar cells. I also wanted to discuss one more thing. We will not have a long session today, but before we end that, I wanted to discuss one thing. Just a second. Yeah, and then about that limit, which is also an important, your Shockley.
Sir, SQ limit, Shockley Poisson limit.
Yep. SQ limit. So what does this put a limit on? First question.
Maximum efficiency, sir.
maximum efficiency of a solar cell, right? That's using a single
Yes,
PN
sir.
junction to collect power. Okay, so and what is the theoretical maximum efficiency of a single junction solar cell? Say, suppose you talk about silicon.
32%, sir, I think. 32 or
Yeah,
33%.
yeah, it's if I remember it correctly, it's around approximately it's 33%, somewhere around there. Okay, and
Yes, yes, sir.
and just a second. So the key factors that determine this limit are the band gap energy, right? What is the band gap energy? And it turns out that the optimal band gap energy for a single junction solar cell is around 1. The optimal band gap, I guess I would write EGO. It's around 1.34 electron volt. Okay, that what that does is that maximizes the extraction of the energy from the sunlight or the falling photons. Okay, and okay, I'm talking about the key factors, right? The band gap is one. Okay, it turns out there is an optimal value. What about other? Are there any other key factors that uh,
Yes, sir.
determine this limit? What else?
Yes, sir. Sir, electron affinity.
Electron affinity. Okay, I would say that is a material specific thing, right?
Yes, material.
And
Sir,
we are already
NAND,
taking care with
NAND,
this. Doping?
doping.
I mean, you can say yes because doping might impact it because the energy loss mechanisms is one key factor in SQ limit, and uh, the thermal losses, the spectral losses, your uh, parasitic resistance losses do affect this limit. So, if your doping affects either of them, then that is one key factor that affects this. And apart from that, your solar spectrum is also one key factor, right? Your efficiency limit, this SQ limit, right? What we calculated or what we stated, this is calculated using your air mass 1.5 solar spectrum, okay, which represents your solar irradiance at the Earth's surface. So AM is also, this is 1.5 AM. I know you might be knowing this, but still I thought I would mention it. And why is this crucial? Why is this SQ limit crucial?
Because, sir, it can give some reference, sir, and the receive power will be maximum to SQ limit, sir. মানে
Okay, I mean, I
solar
would
cell.
take your first point. I mean, that was pretty close to the answer. So the reason is if you'll understand more about this SQ limit, that would be crucial for your R&D in solar cell, right? Because this SQ limit would put as a benchmark against which your performance of upcoming or new solar cell technologies can be compared. Okay, this is what? This is your theoretical maximum efficiency. Then there is experimental efficiency, what is practically achieved. This is theoretically, right? You cannot exceed this theoretically. Okay, but uh, how? So this would act as a reference, right? We'll try to make our what? We'll try to make the efficiency, the obtained efficiency, the experimentally measured efficiency of a solar cell as close as possible to this, right? So that is
Yes, sir.
one thing that is one way rather this SQ limit will matter a lot, and also while this represents a theoretical upper bound, right? This is a theoretical maximum limit. There are lots of ongoing efforts to develop new solar cell technologies that can potentially exceed this 33% limit. Okay, so do keep this in mind as well. For example, multi-junction solar cells. Uh, I'm not sure if Sir has discussed them. Probably he would have discussed because I guess that is one course content. Is there?
No, sir. I think only single junction is discussed, sir. I think, sir. I have not yet, sir, visited all the lectures, sir. Hello, sir. Hello.
Hello. Hello.
Screen is not visible, sir.
Sorry, I got disconnected. I mean, my internet connection suddenly disappeared. That's why I was not even knowing if I was audible or not. Uh, just a second, I'll share my screen again. Sorry for the disruption. I'm
No, no,
myself.
sir. Actually, sir, you are from your home or you are in
Yeah, I'm
hostel,
at
sir.
my home. That's why I'm
Yes, yes,
facing
I know
some
that, sir. Actually,
issues.
sir, you have come
Okay.
to celebrate the Eid, sir.
Yep.
But, sir, you are still now, sir. Teach the class.
Yes. Class has to be
We are,
there
we are
regardless
thankful.
of.
We are thankful, sir.
Thank you so much. So what I was saying is that there are ongoing efforts to overcome this limit, right? Your SQ limit, and this uh, there are, for example, solar cells like multi-junction solar cells that are researched currently. Uh, I mean,
These are
with the
also called
aim of,
tandem solar cell, no, sir?
sorry,
These are also called tandem solar cell, no, sir?
tandem sources. I'm not sure about the naming. Actually, I don't know
No,
much
actually,
about
sir,
solar cells, naming at least. I mean, I just had
you
idea about key basic principle working of this, and I thought I should discuss this SQ limit. So, are multi-junction solar cells called tandem solar cells?
no, actually, sir, multi-junction solar cell made
Okay. As far as I know,
hello.
there, uh, yeah, your voice went off.
If
Sorry, I
sir,
was not able.
okay, sir. If sir, multi-junction solar cell made from some two different material like perovskite and silicon, they are
Yeah.
called tandem solar cell.
Okay, fine. Yeah, that is what I was referring to by multi-junction solar cells. Yeah, those, I mean, you can read about them in literature, or let me do one thing. I'll attach few papers with these slides where where this would be discussed, right? SQ limit, how this has been overcome. Okay, that I would try
Okay, sir.
to
Okay.
add in the lecture slides.
Sir,
Okay.
your sir domain of research sir is different from solar cell, I think.
It's way different from solar cells. I work on modeling of semiconductor devices, specifically compact modeling. So, yeah, I mean, I work on industry standard model, BSIM bulk. I'm not sure if you would be knowing about that. So, that is an industry
So,
standard
sir,
model for bulk MOSFET. Yeah,
sir, is this modeling, sir, is use some special software is there, sir?
I
Silva
was not able
AutoCAD.
to. Could you repeat? Could
Is
you
this
repeat your query
modeling?
again? Yeah.
Is this modeling requires some special kind of software?
Especially type of software. If you talk about compact modeling specifically, yes, I mean we do need some simulators, right, to simulate circuits. So, for example, you have Spectre simulator. So you can say that is a kind of a special software, but it's simulator, right? That is a licensed simulator. I mean, you won't have that freeware. An example of a open source simulator that is free is ngSpice, right? We do work with spice simulators. So if you are interested in uh, exploring this, you can probably explore ngSpice. That is free and open source. And apart from that, HSpice is a simulator that we use that is also commercial and that is licensed. And ADS is a simulator. Okay, these three are the simulators. And apart from that, there is a parameter extraction tool that we heavily use. That is IC cap software. So these
Okay, okay,
are
okay.
some softwares that we use in this area.
No, sir. Actually, I want to know that there are
Okay.
several models. Modeling is also available for solar cell also there. As my
Yes,
domain
yes,
is
yes.
related to domain is related to solar cell. So
Okay.
sir, I think in actually you are doing modeling in semiconductor. As solar cell is
Yeah.
also all the solar cell are made from semiconductor. So there is also
Uh,
compact modeling is there.
okay, yes, there would be some compact modeling. I mean, I'm aware of compact modeling of organic thin film transistors. I mean, I have worked on that as well. But solar cell specifically, I'm not sure if we have a compact model. You could be right. There would probably be a compact model for solar cell as well, because solar cell is a part of a circuit and we are interested in simulating a circuit that would have a solar cell. So yes, I mean, so are you interested in working uh, on
Yes,
compact
sir,
modeling of solar
100%,
cells?
sir. Actually,
Okay,
sir,
okay,
no,
okay.
sir. Actually, sir, I just want to tell you that uh,
Yes.
this course is we can join this course regarding to this is a coursework in kind of some state universities.
Okay, 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 okay,
And
okay.
sir, the
Understood.
pace of this course is quite difficult for us. Means we are I am a working candidate,
I
and
can understand. I can
I
understand.
I do sir part-time PhD in a university. So, sir,
Okay, okay,
actually,
okay.
to cope up, I am already discussed with some friends, sir, who are already joined here. Just
Okay.
match with the pace is quite difficult for us, sir. Because, sir, every week
Correct,
we
correct.
have to attend four classes and four lectures are there. So it
Per
is
week,
quite
right?
difficult for
Per week.
yes, sir, per week, sir. Four
Mm-hmm.
classes done by you and some other faculty, sir, other sir, research scholars. And
Okay, okay, okay.
after that, there will be teacher lecture, and this is quite difficult for us, sir, to continue the pace of the course, sir. We are
Okay,
very
I
much thankful
understood.
that sir, you guys are awesome, sir. I am never ever seen guys like you to teach like this.
Thank you, thank you,
But
thank you so much.
but sir, I am very upset one point that if I am qualified for the subject because the pace is quite high, sir. For
I
us,
can
sir.
understand. I can understand. I mean, since you said that you are, I mean, working or doing this part-time, right? You are pursuing a part-time PhD and doing your work or job. I mean, there was one more fellow, I guess, Sanjeev Karji said this at the start of the session that what if he's not able to come up for the exam if the exam schedule clashes with the job. So I assume he is on the similar lines as well. He's
Yes,
also pursuing it part-time.
he is located near to me, sir. He is
Okay,
one
okay, okay,
means
okay. So
one
you
of my
both
seniors,
know each
sir.
other. Do you both know each other then?
One day, sir, class is held little bit of late, sir. We are both are
Okay,
joined, sir. We are talk with each other and we can consult that the how to qualify the exam, sir. Because sir,
okay,
concept
okay.
is very means essential, sir. I know that. But the
Uh-huh.
course is start little bit of sir late, but we are joined little bit late, sir. And
Okay.
what pace, sir, you could take today, your session will be very short, sir. But
Yeah,
before
yeah, yeah.
that, you can take 1 and 30 minutes session. So,
Mm-hmm.
sir, to understand every concept through online, there is some glitches there are some network issues there, some sound issues
Yes.
are there, and the concept is very sir in depth, sir. I means in our knowledge, sir. I think
Yeah, I
you
can
have
understand. I can understand that. Also, one more thing. I mean, the problems and what should I say? The questions that I discussed for around first 8 weeks, I tried to show you the tough problem. So think that in exams, the difficulty of the problems would be less than the difficulty that was there in my sessions. Even if you would have compared the problems of my sessions with other TAs, in the course, you would have understood this. I mean, I tried to show you the difficult problems so that if you are able to, solve that or understand them, then doing easy problems would obviously be easy. That was the
Sir,
idea. That's why yeah.
sir, if you stop recording, sir, I have
Okay,
discussed with two.
I'll stop. I'll stop the recording just a second.